We'll start in 1 minute. Today we'll continue the final exam review. The final exam is on Monday, May 3rd from 10 a.m. to 12 p.m. Here we got to this problem. Determine the radius and interval of convergence of each power series. So this power series, the terms are x plus 2 to the n divided by n. N goes from 1 to infinity. So to find the radius and interval of convergence, let's use the ratio test. So we'll take the limit of the ratio of the absolute value of the n plus first term divided by the nth term. So we have a complex fraction, x plus 2 to the n plus 1 over n plus 1 divided by the nth term, which is x plus 2 to the n over n inside the absolute values. In the next step, we simplify the complex fraction. We'll write it as the absolute value of x plus 2 to the n plus first over n plus 1, and then times n over the absolute value of x plus 2 to the n. The absolute value of x plus 2 to the n plus first divided by the absolute value of x plus 2 to the n. That simplifies to the absolute value of x plus 2 to the first. And then we're multiplying that by n over n plus 1. The limit of this is equal to, since the limit of n over n plus 1 as n goes to infinity is 1, and x plus 2 is unaffected by n, this limit is the absolute value of x plus 2. And when we use the ratio test, we write that less than 1 because that's, according to the ratio test, when we get convergence. And so negative 1 is less than x plus 2, which is less than positive 1. Solve this for x by subtracting 2 from each of the three parts. We get negative 3 is less than x, which is less than negative 1. The length of this interval is 2, so that means the radius of convergence is 1. And then we need to determine if one or the other of the endpoints are included. So check the endpoints. When we check x equals negative 3 in the original series, replace x with negative 3, we get the alternating series. Negative 3 plus 2 is negative 1 to the n over n. It's the alternating harmonic series, and it is convergent. So that means we will include negative 3, the other endpoint negative 1. In the original series, replace x with negative 1. Negative 1 plus 2 is 1. So this time we get the harmonic series, which is divergent. Okay, so the interval of convergence in interval notation is bracket negative 3 comma negative 1 parenthesis. In the next example, find the radius and interval of convergence. So this time the terms in the series are 2 to the n times x to the n divided by n factorial. And n ranges from 0 to infinity. Well, let's use the ratio test again. So this time we have the limit as n approaches infinity of 2 to the n plus 1 times x to the n plus 1 over n plus 1 factorial, and then divided by 2 to the n times x to the n over n factorial. This is all inside the absolute values. Then we'll simplify the complex fraction. So we have 2 to the n plus 1 times the absolute value of x to the n plus 1 over n plus 1 factorial, and then times n factorial over 2 to the n times the absolute value of x to the n. Two to the n plus 1 over 2 to the n simplifies to a factor of 2 in the numerator. And the absolute value of x to the n plus 1 divided by the absolute value of x to the n, that simplifies to the absolute value of x in the numerator. And then we'll write n factorial in the numerator, and then in place of n plus 1 factorial, we write n plus 1 times n factorial. So the n factorials cancel. And the limit of 2 times the absolute value of x divided by n plus 1, this limit is equal to 0 for all values of x. So for all real numbers x. So that means the radius of convergence is infinity, and the interval of convergence is from negative infinity to infinity. All right, the next part. For any real number x, determine the limit of x to the n divided by n factorial as n goes to infinity. Do this first by finding the interval of convergence of a related power series. Well, the power series that works best in this case is just the series from n equals 0 to infinity of x to the n over n factorial. So let's find the interval of convergence for this series. So let's just use the ratio test again. So we compute the limit as n approaches infinity of the absolute value of x to the n plus 1 over n plus 1 factorial divided by x to the n over n factorial, all in the absolute values. Then simplify the complex fraction. So in the numerator, we have the absolute value of x to the n plus 1 times n factorial. In the denominator, we have the absolute value of x to the n times n plus 1 factorial. Okay, so the absolute value of x to the n plus 1 divided by the absolute value of x to the n simplifies to the absolute value of x in the numerator. And then we'll write n factorial in the denominator, replace n plus 1 factorial with n plus 1 times n factorial. And n factorial divided by n factorial equals 1. So this limit, as n approaches infinity, of the absolute value of x over n plus 1. This limit is equal to 0 for all real numbers x. So the series converges for all real numbers. So in other words, the interval of convergence is negative infinity to infinity. So that tells us what the limit of x to the n over n factorial is. The limit of x to the n over n factorial is equal to 0 for all real numbers x. So bonus points. Why can we say that? So I'll give you 10 or 15 seconds to answer. So how do we know that this limit is equal to 0 for all real numbers x based upon what we did before that? Well, on page 713 of the textbook, Theorem 6, this theorem says if the series of the a sub n terms converges, then the limit of the sequence a sub n is equal to 0 as n approaches infinity. All right, let's move on to the next page. So we'll refresh our memories to see if we can write down the Maclaurin series. 1 over 1 minus x, that's just 1 plus x squared plus x to the third and so on. So in sigma notation, the sum from n equals 0 to infinity and the terms are x to the n. The hard way to do this, if you don't remember it, is just to use the definition of a Maclaurin series. So Maclaurin series have this form. The coefficients are the nth derivative of the function f evaluated at 0 divided by n factorial. And those coefficients are multiplied by x to the n. So if you forget a particular formula, you can still figure out what it is. The Maclaurin series for e to the x is 1 plus x over 1 factorial plus x to the second over 2 factorial, and so on. So in sigma notation, from n equals 0 to infinity, we just write x to the n over n factorial. And we recall that 0 factorial is just defined to be 1. For sine of x, sine of x is an odd function, so that can help us remember what the Maclaurin series is for sine of x. It's alternating, and it's x minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial, and so on. And in sigma notation, we can write it starting at n equals 0, and it's alternating, so we have negative 1 to the n, and then x to the 2n plus 1 divided by 2n plus 1 factorial. For cosine of x, the Maclaurin series, cosine is an even function. So just one other comment about sine of x, it's an odd function, so turns out that the exponents on the variable parts are all odd integers. For cosine of x, the first term is 1, and then after that it's minus x to the second over 2 factorial plus x to the fourth over 4 factorial, and so on. So in sigma notation, it's alternating. So if we start at n equals 0, we need negative 1 to the n minus 1. And then the terms are x to the 2n divided by 2n factorial. Here, the natural log of 1 plus x. Well, if you're like me, I often don't immediately remember. So I can use things that I do remember to help me find the Maclaurin series for the natural log of 1 plus x. So we know that the derivative of the natural log of 1 plus x is equal to 1 over 1 plus x. And we can think of that as 1 over 1 minus negative x. And then if we remember what to do with this, 1 over 1 minus negative x, we can write this as 1 plus negative x to the first plus negative x to the second plus negative x to the third, and so on. And then write it as 1 minus x plus x squared minus x to the third plus x to the fourth, and so on. So if this is the derivative of the natural log of 1 plus x, then the natural log of 1 plus x can be found by finding the antiderivatives of this series. So the antiderivative of 1 with respect to x is x, and then minus x squared over 2, then plus x to the third over 3, then minus x to the fourth over 4, and so on. So we can write this. We can start this at n equals 1 if we want. And it's alternating, so we write negative 1 to the n minus 1. And then we just have x to the n over n. The Maclaurin series for 1 plus x to the k. So this is the series that we get is called the binomial series. So the first term is k choose 0, which is just equal to 1. And then it's k choose 1 times x to the first, and plus k choose 2 times x to the second, and so on. So in sigma notation, it can be written this way. But you'll want to be reminded of what each of those coefficients is. So k choose 0 is just 1. K choose 1 is k divided by 1 factorial, and then times x. K choose 2 is k times k minus 1 divided by 2 factorial times x to the second, and so on. K choose 3, we have 3 factors in the numerator, k times k minus 1 times k minus 2, and divide by 3 factorial. And then another way to write the sigma notation is to write, instead of k choose n for the coefficients, write those as k times k minus 1 times k minus 2, and so on. The nth factor is k minus n plus 1. This is all divided by n factorial, and then times x to the n. Okay, the next page. So at the very top, find an infinite series for the natural number e. So let's just rewrite what e to the x is. E to the x is 1 plus x over 1 factorial plus x squared over 2 factorial, and so on. So the number e just is e to the first. So in this Maclaurin series for e to the x, just replace x with 1. So we get 1 plus 1 over 1 factorial is 1, and then plus 1 over 2 factorial, and so on. So if you want to write some of those numbers out, you can write 1 plus 1 is 2, and then plus 1/2 plus 1/6, because 3 factorial is 3 times 2, and then plus 1 over 24, and so on. Okay, and the next one, find power series for 2x over 1 minus x squared, and then a power series for the indefinite integral of 2x over 1 minus x squared. So if you need to start at ground zero, just remind yourself first that 1 over 1 minus x is 1 plus x squared plus x to the third, and so on. And then you can write the power series for 1 over 1 minus x squared. So for this, we just replace x with x squared. So we get 1 plus x squared, and then plus x squared squared is plus x to the fourth. And then x squared to the third is x to the sixth, and so on. So if you want to write the sigma notation starting at n equals 0, then the terms are x to the 2n, and that's it. Okay, then 2x over 1 minus x squared, if we just multiply the series for 1 over 1 minus x squared by 2x, we'll get that series. So term by term, we multiply by 2x, so we get 2x plus 2x to the third plus 2x to the fifth plus 2x to the seventh, and so on. So in sigma notation, you can write this n from n equals 0 to infinity. 2 times x to the 2n minus 1. That's not what I want. I want 2n plus 1. Because when n is 0, I get x to the first. When n is 1, I get x to the third. Yeah, so that's the sigma notation. And then finally, the power series for the integral of 2x over 1 minus x squared. We just find antiderivatives term by term of the series above, so we get x squared and then 2 times x to the third, or x to the fourth over 4, plus 2 times x to the 6th over 6, plus 2 times x to the 8th over 8, and so on. But we can simplify these, and it works out pretty nicely. We get x squared plus x to the 4th over 2, plus x to the 6th over 3, plus x to the 8th over 4. So you get the picture, and then in sigma notation, I'm going to start at n equals 1. So we get x to the 2n over n. Okay, the next problem says use series to evaluate the limit. So we have this limit of sine of x minus x over x to the third as x approaches infinity. Okay, so if we're going to use series to do that, remember what sine of x is. Sine of x is x minus x to the third over 3 factorial plus x to the 6th. What am I doing? X to the 5th over 5 factorial minus x to the 7th over 7 factorial. And so sine of x minus x, we just get rid of the x. And then if we divide each of the remaining terms by x to the third, we can write down a series for sine of x minus x over x to the third. Okay, so this x is gone because we subtracted x, and then we divide each of those terms by x to the third. So this one becomes negative 1 over 3 factorial, and then plus x squared over 5 factorial minus x to the 4th over 7 factorial, and so on. And then when we take the limit, as x goes to 0, there's only one term that does not go to 0, and that's negative 1 over 3 factorial, or negative 1/6. So that's all there is to that one. So I don't know about you, but it's not obvious to me that this limit equals negative 1/6, aside from looking at the series. Okay, let's look at the next page. So for this one, find the degree 3 Taylor polynomial of f of x equals sine of x at a equals pi over 6. Okay, so to find the coefficients, I'll just rewrite that f of x is equal to sine of x, and f evaluated at pi over 6, sine of pi over 6 is 1/2. Then we need the first derivative of sine, which is just cosine of x. And then we evaluate the first derivative at the value of a, pi over 6. And cosine of pi over 6 is the square root of 3 over 2. Then the second derivative, the derivative of cosine is negative sine of x. So we evaluate the second derivative at pi over 6. And the negative of sine of pi over 6 is negative 1/2. And then finally, the third derivative, the derivative of negative sine of x is negative cosine of x. And then the third derivative evaluated at pi over 6 is negative square root of 3 over 2. So just a reminder of the Taylor series, or the Taylor polynomial, the Taylor coefficients have the form the nth derivative of f evaluated at a divided by n factorial. And then those are multiplied by the binomial x minus a to the n. Okay, so the degree 3 Taylor polynomial, the first term is just f of a, which is f of pi over 6 or 1/2. And then the next term, the first derivative evaluated at a divided by 1 factorial, and then times x minus a. So this one is the square root of 3 over 2 times x minus pi over 6. Okay, and then the next term, so the second derivative of f evaluated at a equals pi over 6 is negative 1/2. So we'll write minus 1/2 divided by 2 factorial times the binomial x minus pi over 6 to the second. And then the last term in the Taylor polynomial, so we have minus the square root of 3 over 2 divided by 3 factorial times x minus pi over 6 to the third. Okay, so we can write it so that it looks a little bit neater. The first two terms are okay, 1/2 plus the square root of 3 over 2 times x minus pi over 6. And then minus 1/2 divided by 2 factorial is just minus 1/4 times x minus pi over 6 to the second. And then the next one, the square root of 3 over 2 divided by 3 factorial, we can write this as the square root of 3 over 12, and then times x minus pi over 6 to the third. Yeah, that's all there is to that. The next one, find the Maclaurin series for f of x equals 1 minus 3x to the negative 5. So we can remind ourselves of the general form. 1 plus x to the k is this series. K choose 0 and then times x to the n. So in place of x, we're going to put negative 3x. So think of that as 1 plus negative 3x to the negative 5. Okay, so the first term, k choose 0, which is 1, and then plus k choose 1. I'll replace k with negative 5 in a minute. So this one is going to be multiplied by negative 3x to the first, and then k choose 2 times negative 3x to the second, and so on. So the value of k is negative 5. So negative 5 choose 0 plus negative 5 choose 1 times negative 3x to the first plus negative 5 choose 2 times negative 3x to the second. I'll just write out a couple more terms. Negative 5 choose 3 times negative 3x to the third, and then plus negative 5 choose 4 times negative 3x to the fourth, and so on. So let's get an idea what this Maclaurin series looks like. Negative 5 choose 0, that's just 1. And then we have negative 5 divided by 1 factorial times negative 3x. And the next term, negative 5 choose 2. So it's negative 5. Then the next number should be negative 5 minus 1, which is negative 6. And then divide by 2 factorial. And the term negative 3x to the second is 9x to the second. Okay, then the next term, the next coefficient, negative 5 choose 3. So 3 tells us we need 3 factors, negative 5, negative 6 times negative 7. And we divide by 3 factorial. And the term negative 3x to the third is negative 27x to the third. And we'll do just one more. Negative 5 choose 4. We need 4 factors. So starting with negative 5 times negative 6 times negative 7 times negative 8 divided by 4 factorial. And then the term negative 3x to the fourth is 81x to the fourth. So the next line this will be our last one. So 1 plus 15x. And then the next one, negative 5 times negative 6 divided by 2 is 15. 15 times 9 is 135. So we get 135x to the second. And then the next one, the coefficient will be positive again because we have an even number of negative factors. So negative 5 times negative 6 times negative 7 divided by 3 factorial is negative 35. And then negative 35 times negative 27. For now, I'm just going to write 35 times 27. You can figure that out. And then times x to the third. And then the next one, so it's the coefficient will be, that's supposed to be negative 8. The coefficient will be positive again. So this time we get 70 times 81 times x to the fourth. And there's more, and this doesn't look like it's that easy to find a formula for the sigma notation. So if you can come up with 4 or 5 or 6 terms for the Maclaurin series, that's pretty good. Okay, let's look at the next problem. Approximate the function f of x equals x times sine of x at a equals 0 with a degree 4 Taylor polynomial. Then use Taylor's inequality to estimate the accuracy on the interval where the x values come from -1 to 1. Well, since a is equal to 0, this is just a Maclaurin polynomial of degree 4. So we have to find 4 derivatives. So first note, f of x is x times sine of x, and f of 0 is 0. Then the first derivative, we use the product rule. So the derivative of x times sine of x is sine of x plus x times cosine of x. Evaluate the first derivative at 0, we get 0 again. The second derivative of f, we get cosine of x, and then use the product rule on this part. So we get plus cosine of x, and then minus x times sine of x. Let's simplify the second derivative, since cosine of x plus cosine of x is 2 times cosine of x. And then evaluate the second derivative at 0. This time we get positive 2. And then the third derivative, so take the derivative of 2 cosine of x minus x times sine of x. So this time we get negative 2 times sine of x. Then use the product rule again, we get minus sine of x. And then minus x times cosine of x. Simplify this by combining the like terms, we get negative 3 sine of x minus x times cosine of x. And then when we evaluate the third derivative at x equals 0, we get 0 again. Hey, one more derivative, the fourth derivative. This time we get negative 3 times cosine of x, and then minus cosine of x, and plus x times sine of x. Combine the like terms, we get negative 4 times cosine of x plus x times sine of x. And the fourth derivative evaluated at 0 is just negative 4. So it looks like we'll have time to write down the degree 4 Taylor polynomial. At a equals 0. So f of 0 is 0. F of 1 is 0. sorry, the first derivative evaluated at 0 is 0. The second derivative evaluated at 0 is 2. So we have 2 over 2 factorial times x minus 0, or just x to the second. The third derivative evaluated at 0 is 0. And then finally, we get the fourth derivative evaluated at 0 is negative 4. So this is minus 4 over 4 factorial times x to the fourth. And so the degree 4 Taylor polynomial is x squared minus 1/6 x to the fourth. Okay, we ran out of time, so go ahead and sign in for attendance.